Welcome back. In this video lecture, we are going to solve one more the free longitudinal vibration problem, right? So in this case, the problem here, the problem statement here, a mass is suspended from a spring system as shown in figure, right? The mass is suspended with the spring system. That's the figure all given here, right? We determine the natural frequency. So that means we need to calculate the natural frequency of this system, right? And he has given the different springs. Can you see here? So the K1, K2 and K3 are the spring constants and M is the mass of the system. And the numerical values he has provided. K1 is equal to 5000 Newton meter and K2 is equal to K3 is equal to 8000 Newton meter and M is equal to, the mass is equal to 25 kg. Right? In this case, we can see here. So K1, K2, K3, they are not in a parallel, they are not in a series. Can you see here? The K2 spring and the K3 are in parallel condition. Once we are forming these two in the equivalent spring, then K1 and KE23 are going to be the series condition. Right? And we need to draw the equivalent spring constants for this one. For getting an idea, I am going to draw a simplified diagram for this one. So this is going to be the spring 1, K1 stiffness, and the next one I am going to be taking equivalent spring constant for the mass of this one, that is going to be K2, 3. Right? In this case 2, 3, the two springs we are taking. What is this one? This is equal to K1 plus, K2 plus K3. And once you simplify this one, we will get another simplified diagram for this one. The single spring, this is the mass K, E, 1, 2, 3. Right? And here we do have the parallel and here we do have the series. So then KE 1, 2, 3 is equal to, what's the formula we are going to getting from this one? 1 KE 1, 2, 3, that is equal to 1 by K1 plus 1 by KE 2, 3. So this way we are going to be calculating the KE 1, 2, 3 and then we can calculate the natural frequency of the system. Right? And for coming to this diagram, okay, so what is the value of K2, 3? This is the equivalent spring constant for the spring 2 and 3, that is equal to K2 plus K3, that finally 8000 Newton plus 8000 Newton meter, 16,000 Newton meter, we got it. Once you got it, then we need to go for the series conditions. That means K1 and KE2, 3. So that's equation I am rewriting here. KE 2, 3, 1, 2, 3, that is equal to 1 by K1 plus 1 by KE 2, 3. Right? And then this is going to be 1 by 5000 Newton meter plus 1 by 16,000 Newton meter. And then finally KE 1, 2, 3 is equal to, what is the, how much value we are going to be getting? So that is equal to 3,809 Newton meter we will get it. So the KE, the total equivalent of these three springs is equal to 3,809 Newton meter. Once you calculate it, then we need to write the natural frequency of this system. That's going to be F is equal to 1 by 2 pi square root of KE by M. Right? Once we are going to be substituting this equation, these values, KE is equal to 3,809 Newton meter by M is equal to 25 kg. Then what is the F value we are going to be getting? That's going to be 1.96 Hz. And this is going to be your natural frequency of this system. This way we are going to be calculating. In this figure, they given the three springs, the two springs they connected in parallel, one spring they connected in the series. So on that basis, we have drawn the simplified diagram, spring and mass system. Then we calculated the natural frequency. Once you calculated the equivalent spring stiffness, then we can substitute in the natural frequency, we can get that equations. Okay, thank you.